This is Into the Multiverse with Josh Peck.
Hey everybody, let's face it, quantum physics is confusing. So in this video, I wanted to lay out just a few things to keep in mind that'll make the whole process go a lot easier to understand, and it'll help you enjoy the show more, I think. Now, I came across an article in Forbes written by Chad Orzel, who's he is a professor of quantum physics and pop science author and blogger. And I think he's got a book coming out in December 2018 this year called Breakfast with Einstein, the exotic physics of everyday objects. I came across one of his articles and I just thought it was great. It's called 6 Things Everyone Should Know About Quantum Physics. I think there's actually 4 things in the article, unless I miscounted. Math is not my strong suit. But I thought it was so brilliantly written that it's written in a way that for hardcore quantum physics enthusiasts, you're going to get a lot out of it because there's some technical language in here. But also, like, if you just want the basics and you just want to know the cool stuff about it, and the important stuff about it, there's a lot of language for the layman in here too. And I thought it was a really good dichotomy of both. Well, it blended well. I don't know, dichotomy might not be the exact right word, but it blended really well. So I wanted to kind of go through this article and talk to you guys about this because, I mean, you know, like I said, we'll be honest, quantum physics is usually just intimidating from the get-go. It's only intimidating. I mean, it's kind of weird and can seem counterintuitive, even for physicists who deal with it every day, but it's not incomprehensible. So if you're reading something about quantum physics, there's really just a handful of key concepts about it that you should keep in mind. And do that, and you'll find that quantum physics is a lot easier to understand. So we'll run through a couple of these. The first thing we can talk about is that everything is made of waves, also particles. So there's lots of places to start this sort of discussion, and it's as good as any. Everything in the universe has both particle and wave nature at the same time. So everything in the universe has a wave nature, but everything also has a particle nature. Now, that seems completely crazy, but it's actually an experimental fact that has been worked out by, surprisingly, a lot of familiar processes. We've done episodes on this show before about the quantum the double slit experiment, the quantum experiment. There's also the quantum eraser, which talks about entanglement, which we'll deal with in a little bit. But it talks about it shows that everything is made of waves and particles. Now, describing real objects as both particles and waves is necessarily somewhat imprecise. So properly speaking, the objects described by quantum physics are neither particles nor waves, but this third category that shares some properties of waves, a characteristic frequency and wavelength, some spread over space, and some properties of particles. They're generally countable and can be localized to some degree. Now, this leads to some lively debate within the physics education community about whether it's really appropriate to talk about light as a particle in intro physics courses, not because there's any controversy about whether light has some particle nature, but because calling photons particles rather than excitations of a quantum field might lead to some student misconceptions. Now, some don't agree with that because many of the same concerns could be raised about calling electrons particles, but it makes for a reliable source of blog conversations, at least. Now, this door number 3 nature of quantum objects is reflected in the sometimes confusing language physicists use to talk about quantum phenomena. So the Higgs boson was discovered at the Large Hadron Collider as a particle, but you'll also hear physicists talk about the Higgs field as a delocalized thing filling all of space. And we've done episodes on quantum field theory on this show before, so you can go back in the archives and check those out if you're interested. But this happens because in some circumstances, such as collider experiments, it's more convenient to discuss excitations of the Higgs field, or little quantum fluctuations in the Higgs field, in a way that emphasizes the particle-like characteristics, while in other circumstances, like general discussions of why certain particles have mass, it's more convenient to discuss the physics in terms of interactions with a universe-filling quantum field. It's just different language describing the same mathematical object. You can think of it like that. Now, it's right there in the name. The word quantum comes from the Latin for how much and reflects the fact that quantum models always involve something coming in discrete amounts. So the energy contained in a quantum field comes in integer multiples of some fundamental energy. So for light, this is associated with the frequency and wavelength of light. High frequency, short wavelength light has a large characteristic energy, while low frequency, long wavelength light has a small characteristic energy. In both cases, though, the total energy contained in a particular light field is an integer multiple of that energy. So 1, 2, 14, 137 times. It's never a weird fraction like 1.5 or pi or the square root of 2. This property is also seen in the discrete energy levels of atoms and the energy bands of solids. Certain values of energy are allowed, others are not. So atomic clocks work because of the discreteness of quantum physics, using the frequency of light associated with a transition between two allowed states in cesium to keep time at a level requiring the much discussed leap second that's added every now and then. Now, ultra precise spectroscopy can also be used to look for things like dark matter, and it's part of the motivation for a low energy fundamental physics institute. Now, this isn't always obvious. Even some things that are fundamentally quantum, like black body radiation, for example, appear to involve continuous distributions, but there's always a kind of granularity to the underlying reality if you dig into the mathematics, and that's a large part of what leads to the weirdness of the theory. Now, here's another thing to keep in mind. Quantum physics is probabilistic. It's based in probabilities. So one of the most surprising and historically, at least, controversial aspects of quantum physics is that it's impossible to predict with certainty the outcome of a single experiment on a quantum system. Now, when physicists predict the outcome of some experiment, the prediction always takes the form of a probability for finding each of the particular possible outcomes, and comparisons between theory and experiment always involve inferring probability distributions from many repeated experiments. So the mathematical description of a quantum system typically takes the form of what's called a wave function, generally represented in equations by the Greek letter psi, which looks like a candelabra with three prongs, sort of. There's a lot of debate about what exactly this wave function represents, and it basically breaks down into two main camps. There are those who think of the wave function as a real physical thing. The jargon term for these people is ontic theories, leading some witty person to dub their proponents Scientologists. Get it? Scientology, Sci, Greek letter. Ha ha ha. That's a physics joke. A lot of them are corny. But and those who think of the wave function as merely an expression of our knowledge or lack thereof regarding an underlying state of a particular quantum object, or that's called the epistemic theories. Now, in either class of foundational model, the probability of finding an outcome is not given directly by the wave function, but by the square of the wave function. So loosely speaking, anyway, I mean, the wave function is a complex mathematical object, meaning it involves imaginary numbers like the square root of -1. And the operation to get probability is slightly more involved, but square of the wave function is enough to just get the basic idea. So this is known as the Born rule, after German physicist Max Born, not Jason Bourne, Max Born, who I don't think led quite as exciting of a life, but still discovered some pretty cool stuff. He first suggested this in a footnote to a paper in 1926, and strikes some people as an ugly ad hoc addition. I mean, there's an active effort in some parts of the quantum foundations community to find a way to derive the Born rule from a more fundamental principle. But to date, none of these has been fully successful, but it generates a lot of interesting science. So this is also the aspect of the theory that leads to things like particles being in multiple states or multiple places at the same time. So all we can do, all we can really predict is probability. And prior to a measurement that determines a particular outcome, the system being measured is an indeterminate state that mathematically maps to a superposition of all possibilities with different probabilities. So whether you consider this as the system really being in all states at once or just being in one unknown state, that depends largely on your feelings about ontic versus epistemic models, though these are both subject to constraints from the next item that we're going to talk about, which is quantum physics is non-local. So the last great contribution Einstein made to physics, here's a bit of trivia for you, was not widely recognized, mostly because he was wrong. So in a 1935 paper with his younger colleagues, Boris Podolsky and Nathan Rosen, the EPR paper is what it was called. Einstein provided a clear mathematical statement of something that had been bothering him for quite some time, an idea that we now call entanglement. Einstein referred to it as spooky action at a distance. The EPR paper argued that quantum physics allowed the existence of systems where measurements made at widely separated locations could be correlated in ways that suggested the outcome of one was determined by the other. So they argued that this meant the measurement outcomes must be determined in advance by some common factor, because the alternative would require transmitting the result of one measurement to the location of the other at speeds faster than the speed of light. And in fact, even to say speeds faster than the speed of light isn't accurate, because there's no speed, there's no time involved. It's at an absolute instant. So even saying faster than light isn't exactly right, but you could sort of think of it that way. But thus, if that were true, then quantum mechanics must be incomplete, a mere approximation to some deeper theory or a local hidden variable theory, one where the results of the particular measurement do not depend on anything farther away from the measurement location than a signal could travel at the speed of light, local, but are determined by some factor common to both systems in an entangled pair, or the hidden variable. Now, this was regarded as an odd footnote for about 30 years, as there seemed to be no way to test it out. But in the mid-1960s, the Irish physicist John Bell worked out the consequences of the EPR paper in greater detail. So Bell was able to show that you can find circumstances in which quantum mechanics predicts correlations between distant measurements that are stronger than any possible theory of the type preferred by EP and R. So this was tested experimentally in the mid-1970s by John Clauser, and a series of experiments by Alain Aspect in the early 1980s is widely considered to have definitively shown that these entangled systems cannot possibly be explained by local hidden variable theory. So the most common approach to understanding this result is to say that quantum mechanics is non-local, that the results of measurements made at a particular location can depend on the properties of distant objects in a way that can't be explained using signals moving at or faster than the speed of light. Now, this does not, however, permit the sending of information at speeds exceeding the speed of light, though there have been any number of attempts to find a way to use quantum non-locality to do that. Refuting these has turned out to be a surprisingly productive enterprise. You could check out David Kaiser's How the Hippies Saved Physics for more details on that. But quantum non-locality is also central to the problem of information in evaporating black holes and the firewall controversy that has generated a lot of activity within the past 3 to 5 years. There are even some radical ideas involving mathematical connection between the entangled particles described in the EPR paper and wormholes. We've also done episodes on this show about quantum entanglement, so you could look up those if you're interested in more. But quantum physics has a reputation of being weird because its predictions are dramatically unlike our everyday experience, at least for humans. That is, but who knows about angels or God or whatever. But this happens because the effects involved get smaller as objects get larger. So if you want to see unambiguously quantum behavior, you basically have to see particles behaving like waves, and the wavelength decreases as the momentum increases. So you can think of it this way: the wavelength of a macroscopic object like a dog walking across the room is so ridiculously tiny that if you expand everything so that a single atom in the room were the size of the entire solar system, the dog's wavelength would be about the size of a single atom within that solar system. So that's how ridiculously small that wavelength would be. But that means that for the most part, quantum phenomena are confined to the scale of atoms and fundamental particles, where the masses and velocities are small enough for the wavelengths to get big enough to observe directly. There's an active effort in a bunch of areas, though, to push the size of systems showing quantum effects up to larger sizes. There's blogs and articles about it online about a bunch of experiments by Marcus Arndt's group showing wave-like behavior in larger and larger molecules. And there are a bunch of groups in what's called cavity optomechanics trying to use light to slow the motion of chunks of silicon down to the point where the discrete quantum nature of the motion would become clear. There are even some suggestions that it might be possible to do this with suspended mirrors having masses of several grams, which would be amazingly cool. So here's another thing to keep in mind. Quantum physics is not magic. This is probably the most important thing because New Agers have latched onto quantum physics and have totally twisted it around and turned it into something that it is not. So the previous point leads very naturally into this one. As weird as it may seem, quantum physics is most emphatically not magic. It's not anything you want to be is so because you want it to be. The things it predicts are strange by the standards of everyday physics, but they are rigorously constrained by well understood mathematical rules and principles. And I promise, ask a New Ager to explain those mathematical rules and principles. They won't be able to do it. Yet a lot of them want to tout all the time about how quantum physics is the answer to their worldview. But so if somebody comes to you with a quantum idea that seems too good to be true, like free energy or mystical healing powers, we did a video recently on this channel about quantum healing, about really quantum biology and how there is actually a very real science called quantum biology that's fascinating. It dictates how birds migrate, even how we use our sense of smell. But there's also a new age concept of quantum biology that involves these weird mystical healing powers, and it's just not real. It's garbage, is what it is. So if somebody comes up to you with stuff like that or impossible space drives or something, it almost certainly is too good to be true. It's not real. Now, that doesn't mean that we can't use quantum physics to do some amazing things. You can find some really cool physics in mundane technology today, but those things stay well within the boundaries of the laws of thermodynamics and just basic common sense. So there you have it. Those are basically the core essentials of quantum physics. I probably left a few things out or made some statements that are insufficiently precise to please everyone, but this ought to at least serve as a useful starting point for further discussion. Now, again, this comes from an article on Forbes by Chad Orzel. He's a physics professor, pop science author, and blogger, and keep an eye out for his book, Breakfast with Einstein, The Exotic Physics of Everyday Objects. But yeah, I wanted to talk about that because every now and then I want to go back to the basics on this channel, give everybody a refresher course. And also we're getting new subscribers all the time. So I want to be able to do that for them too. So, all right, this has been a blast. Make sure you subscribe if you haven't already. And click the bell, because you got to tell YouTube that you want to be notified, and they still might not notify you. But just know that you will get a new episode of Into the Multiverse right here on this channel, youtube.com/Into the Multiverse at 9 a.m. We're also on Roku, Blog Talk Radio, Vimeo, PTL Network. We're everywhere. Into the Multiverse is everywhere. We're easy to find. So Thursday morning, 9 a.m. right here on this channel is the best place to go. All right. I love you all. Thank you so much. And until next week, take care and God bless.
Global experts are now debating whether humanity should fear the rise of AI assassins. Will transhumanism, singularity, and demonically infused killer robots be the last onslaught of Satan in an attempt to destroy every human on Earth? Learn what the Bible has to say on this very urgent topic now in the new, oversized book, Terminated, by legendary author Steve Quayle. In Terminated, you will learn why hundreds of artificial intelligence experts believe that humanity will soon experience gigadeath at the hands of autonomous killing machines. Why hybridizing humans is thrusting us toward a golden age of mythical monsters and godlike humans. And what Jesus declared about God's plan to shorten the days here on earth, because if not, there would be no flesh left alive. Plus, when you order Terminated from the Skywatch TV store, you'll also receive the brand new documentary movie from Gen 6 Productions, Forbidden History Revealed. The Egyptian presence in the Americas and the Pacific Rim, the Great Smithsonian Cover-Up. Now, for the first time in history, you'll watch an eyewitness account of actual Egyptian artifacts and giant skeletons that were excavated from the Grand Canyon and burial mounds across the U.S. and South America, stored for over 100 years in a secret underground Smithsonian warehouse. This full-length feature film also asks the questions: why is the DNA of giant mummies and viable skeletons being extracted by the militaries of the world? Was a living 21-foot giant captured in 1877 with the most unusual features ever noted? And will the giants of yesterday become the super soldiers of tomorrow? These two incredible new works are available together for a special donation of only $50 now at the SkywatchTVStore.com. So don't delay. Order Terminated, the Steve Quayle special offer, online now or call 1-844-750-4985.